Okay, so I'm recording now, but whatever. You missed the first part, but hopefully this will still help, because that was what I talked about was just the basis of everything anyway. So, okay, so let's talk about each type of IMF or intermolecular force here. So dipole, and again, like I said, dipole is a type of and hydrogen bonding is a type of dipole bond. So basically, dipole is when two polar molecules are attracted to one another. Okay, so two polar molecules attract to one another. So for example, HCl, we're talking about gas here because actually in the liquid form, HCl is actually ions, right? So if it's in water, so HCl gas. This is an intermolecular attraction because the chlorine is much more electronegative than the hydrogen. Chlorine is going to pull electron density towards itself. It's going to have a slightly negative charge to it. It's going to have a slightly negative charge to it, and hydrogen is going to have a slight positive charge to it, and there is that interaction here, this dipole-dipole interaction. Okay, the more polar a molecule is, the stronger the dipole-dipole interactions. Okay, the stronger the dipole-dipole interactions. Okay, and when we talk about most of these things, we're only going to be talking about intermolecular forces between like molecules. Okay, so we're talking about like molecules, so looking at boiling point, freezing point, all that good stuff. That's kind of the important part of this. Now, hydrogen bonding is a dipole-dipole intermolecular force. When you have a molecule with a hydrogen that has a partial positive and another molecule with nitrogen, fluorine, or oxygen. Okay, so the highly electronegative elements, if you think about it, those are the most electronegative elements. Nitrogen, fluorine, and oxygen, they're all right there on the top of the periodic table in the corner. Okay. So one thing I always forgot when I was in school was that hydrogen bonding can occur between hydrogen, oxygen, nitrogen, and fluorine. I always forget fluorine and nitrogen, and I would always think oxygen because the best example of hydrogen bonding is water. Okay, water. Hydrogen bonding also occurs in DNA. It occurs in DNA, in the backbone of DNA. So there's nitrogens in the backbone of DNA, and they have hydrogen bonding in there. So hydrogen bonds, these little dots. So oftentimes we represent intermolecular forces with dots because it's not a solid bond. It's an intermolecular force. So we put little dots. Okay. So if they ever asked you to draw hydrogen bonding, an example of hydrogen bonding, you draw something. It would look something like this, where you have oxygen has a slightly negative charge to it, and each hydrogen has a partial positive charge to it. Okay. So this is this symbol here. Oh wait, let me go back. This symbol, that little like weird looking thing, that's a partial. That means partial. It's bigger here. This partial thing. I forget what. It's a Greek letter or Latin letter. I forget which one it is, but it's like a zero with a C on top of it, basically. But that means partial. So you have a partial positive and partial negative. So it's not a full positive, not a full negative. So that hydrogen bond, again, is between the positive hydrogen, negative oxygen. Any questions on dipole, and hydrogen bonding? Is that pretty clear? Okay, that's probably the easiest one. Just talking about two polar molecules attract to one another, right? Pretty easy. Hydrogen bonding is just a specific one where you have hydrogen and nitrogen, hydrogen, fluorine, or hydrogen and oxygen. All right, the next. Ion-induced dipole is a little bit trickier. So think about an ion. an ion has a full positive or a full negative charge, right? Is a full positive or full negative charge. You get an ion and you get a molecule or an atom that has no dipole. That ion comes in. If it's a positive ion, it's going to attract the electrons towards itself. So one side of the molecule now, that nonpolar molecule, will have a slightly negative side to it, and then the other side will be slightly positive. Okay, and this will only be negative and positive. Oh, I'm taking out the garbage. Sound loud. Okay, so this will only be negative and positive as long as that ion is there. Okay, so that's why we call it induced. It's induced by the ion. Okay, the dipole is induced by the ion. The ion induces a temporary charge on the otherwise nonpolar molecule. Now this is so I'm just thinking to myself here, but this is why I don't like to memorize it, because I'm also thinking, like, if you had an ion and a dipole, so if you had an ion and something that had a positive and negative charge, that would actually be a stronger attraction, right? An ion would have a stronger attraction to a polar molecule, right? But we really don't talk about that one too much. And really, why we don't talk about that one too much is because what we're really concerned with here is the interaction between the molecule, the like molecules. Like, do the like molecules, how is their interaction? So when you have an ion come in, now this will cause the non-polar molecule now to have a charge, and now it will interact with other molecules like itself. Okay, now we'll have forces between the molecules like themselves. We don't really consider ions, right, for when we talk about intermolecular forces either. But the ion creates a dipole, and now that dipole can interact with other atoms or molecules that are the same as them. Okay. Intermolecular forces are confusing. Great, right? Okay, next one. So next one is dipole-induced dipole. So if you have a molecule that has a dipole moment, so you have a polar molecule and it interacts with a molecule that is not polar, it will create a temporary dipole for that nonpolar molecule. Pretty simple, right? You have a polar molecule, it interacts with a nonpolar molecule and makes that molecule now have a temporary dipole. It's temporary because it's only going to be there as long as the two are interacting with one another. And we call that dipole-induced dipole. There's going to be a little bit of a trend here, right? Now it's all going to be induced. It's all going to be induced. It's all going to be not usually having a dipole, and then something makes it have a dipole. So we have dipole-induced dipole. So like we had the ion-induced dipole. Now we have dipole-induced dipole. The next one is induced dipole-induced dipole. So we have two nonpolar atoms or molecules that are not polar on their own, but when they interact with one another, their electron clouds tend to move away from each other, create a temporary dipole, and they now have a temporary dipole and are attracted to one another or attracted to other molecules in their mixture there. Okay, and this is typically like those. Why I put London dispersion forces is because typically, if you don't have a dipole, London dispersion, so the electrons are dispersed. That's why we think of London dispersion forces. The electrons are dispersed because they are moved temporarily. Yeah, that's what kind of London dispersion forces are. The forces that make the electrons disperse, and then that connection or that interaction between the two, the intermolecular forces, are those van der Waals forces. But they're kind of used, like I said, they're kind of used interchangeably. London dispersion forces and van der Waals forces are kind of used interchangeably. Okay. That's pretty much it for the types of forces. Now let's see how they're used. So typically the kind of questions you're going to get these like boiling point questions, and this can be applied for boiling point, melting point, and vapor pressure. Just remember that let me write up here. So, like stronger forces is higher boiling point, so stronger forces. So the stronger the intermolecular forces, you get a higher boiling point. A higher melting point. Okay. And a lower vapor pressure. Okay, lower vapor pressure. So just keep that in mind, because we're going to talk. This is specifically about boiling point, but it can be applied to melting point and vapor pressure in the same sense. Okay, so just understand stronger forces mean these things, but really what we're looking at here is just the strength of the forces. Okay. So first thing you got to look at, so you're going to look at like three different things. You're going to look at three different things, and it's kind of actually in this order. Okay, the first one is the strength of the forces. Okay, now typically these questions are not going to ask you for, so I forgot to say this here. Typically they're not going to ask you like what is the boiling point of this or what is the boiling point of that. They're gonna give you like a couple different molecules and ask you which one has the highest boiling point, which one is the lowest melting point, which one is the highest vapor pressure, that kind of thing. Okay, you have to understand that whatever one has the lowest vapor pressure has the strongest force. Whatever one has the highest boiling point has the strongest force. Highest melting point, the strongest forces. Okay? And forces meaning like, actually, we're looking at forces, but all these things come into play. When you look at this type of question, the first thing you want to see, you want to look at is, are the forces, the intermolecular forces, different? Are they different? If the intermolecular forces are different, then you use this to determine right here. Use this to determine, and what we just talked about actually, to figure out if which one has the highest boiling point or the strongest intermolecular forces, right? So we talked about ionic forces actually are the strongest. And sometimes those are considered intermolecular forces, sometimes they aren't. But if they're asking you for boiling point or something like that, then ionic substances will usually have the highest boiling points. Next, you have hydrogen bonding. So if you see hydrogen bonding, that's the next strongest. Then after that, you have dipole-dipole. So whatever one is the most electronegative, whatever one has the biggest electronegativity differences, so the polarity. And then finally, those London dispersion forces, and all of those were, again, we talked about all these ones. So the ion-induced dipole, dipole-induced dipole, and the induced dipole. So that's the first trend. That's the first thing you look at. If those are different, then you use that to determine what is the trend. Which one's the strongest forces? Which one has the highest boiling point? Which one has the highest melting point? All that good stuff. If they all have the same forces, if they all have the same IMFs, then you look at the size. You look at the size of the molecule. Okay? The larger the molecule, so for example, this one here, these all have hydrogen bonds, actually. These all have hydrogen bonds. These ones all have hydrogen bonds. And you'll see that the larger the molecule, the higher the boiling point. The stronger the IMFs, the stronger the intermolecular forces. Okay? So we have all hydrogen bonds. Those types of forces are constant. So the boiling point increases with increased surface area or increased size. This is longer than this one, so it's higher in boiling point, and this one's the shortest. Okay? These ones down here, these all have just LDFs, London dispersion forces, or just induced dipole. All of these are just induced. Just LDFs, straight LDFs. Okay, so the bigger the chain, the higher the boiling point. Long chain, higher boiling point. And then the last one here, these ones all have the same. What do you think? This one would not actually have, I don't believe these have hydrogen bonds. This would be weak. No, these would not have hydrogen bonds. These wouldn't have hydrogen bonds. These would just be LDFs too. Typically, in order for something to have hydrogen bonds, the hydrogen has to be directly attached to an oxygen or a nitrogen. This oxygen doesn't have any hydrogens attached to it, so it's not going to pull electrons away from the hydrogen. So you're not going to, there's no H bonds here. In order to have hydrogen bonds, you have to have the N with an H, O with an H, or F with an H. Or actually, not necessarily with this. Oh, well, yeah, that actually works, but HF actually has hydrogen bond, but this oxygen doesn't have any hydrogens attached to it. When you have what these chains mean, I forgot to mention this, my bad. Basically, these chains, this is a, let me erase some of this so I can make some room here. I forgot to mention what this chain is if you don't know what's going on here. This is actually a carbon attached to 3 hydrogens. And then another carbon attached to 2 hydrogens. And then another carbon attached to 2 hydrogens. And then another carbon attached to 2 hydrogens, and 1 nitrogen. And that's just how we draw organic molecules, is just these chains. Anytime you see, this is just a carbon with saturated with hydrogens. Carbon, 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 all with hydrogens attached to it. It's just the way we draw organic molecules to make it simpler. So hopefully that clarified anything if you were confused about that, what the heck these molecules were. Sorry about that. But yeah, so the larger the molecule, the stronger the intermolecular forces. So first you look at the type of forces, then you look at the size. So type of molecule, then the size. Then the last thing you look at, oh, my computer's lagging. Doesn't like me. It needs to take a nap. My friend in college, he's really good with computers. He does, he used to do computer programming and stuff, and anytime I had problems with my computer, he would help me out. And I'd be like, oh, I just need to give it a rest. I just need to shut it off and let it sit for like 2 hours. He's like, what? That doesn't work. That doesn't do anything. Oh, it works. It works. I think sometimes it just needs to cool down, you know? Because computers work better when they're cool, right? And then if you're running them a long time, they get hot. So I think it kind of messes it up sometimes. But I don't know. It's probably bad science, but. All right, and then last thing. Last one. If the molecules are the same, they have the same intermolecular forces, they have the same number of atoms of each type, then it comes down to their structure. And I don't know if you'll see a problem like this, but I mean, just throw it in there anyway. This is actually from an organic chemistry book, but I don't know, it works the same. So I was like, whatever, this works. But you may or may not see this. The more branched it is, the lower the boiling point. You're going to have less surface area. Okay. If you have a branched, so branched meaning like it's not linear. So this is linear. And this is more branched. I mean, this has a branch too, but this is linear, right? The more branches it has, the less linear it is, the lower the boiling point. So you notice that that's just a lower boiling point. Just think the flatter it is, the longer it is, the higher the boiling point. Okay? Okay, now all this stuff. So just remember that boiling point is when vapor pressure equals atmospheric pressure. So if you lower vapor pressure, if you're lowering the vapor pressure, you're actually increasing the boiling point. So lowering vapor pressure, because intermolecular forces are getting stronger, actually increases the boiling point. Now, if you lower the atmospheric pressure, you lower the boiling point. Okay. Stronger molecular forces, higher the boiling point, lower vapor pressure, and higher melting point. Just remember all those things. So this is going over the different 4 intermolecular forces. Ionic, hydrogen bonding, dipole-dipole London dispersion. Some people consider ionic bonds intermolecular because they're not sharing electrons, and technically their electron clouds are not technically overlapping. So sometimes they consider them. In AP chemistry, they're not going to consider them IMFs. To tell you the truth, they don't consider ionic. So I wouldn't worry too much about that. So hydrogen bonding, again, look for molecules containing OH or NH. HF is the only one. HF is the only one with fluorine that has hydrogen bonds. Okay, because fluorine only forms one bond, so it's not going to connect with anything else. That's the only one with fluorine that's going to have hydrogen bonds. You have to see that N and O, they have to be connected directly to an H. Okay, directly to an H. However, like the oxygen ones are much stronger than the nitrogen ones, as it says there. So NH3 has a boiling point of negative 33, whereas H2O is 100. Okay, so just keep that in mind. Dipole, we talked about that. You don't have to worry about these functional groups or anything. That's all organic chemistry. The size of the charge, again, is electronegativity differences. So we did a worksheet on that. So you're looking at the difference in electronegativity. The greater the difference in electronegativity, the greater the polarity, the greater the dipole-dipole interaction. Okay. Okay. And then again, London dispersion forces, the larger the atom, the larger the molecule, the greater the force. The straighter it is, the greater the surface area of it, the greater the force. If you think of them all like suction cups, that's what he's saying here. So they're very small suction cups. Each individual point of contact is weak, but dozens of them can add up to a strong intermolecular force. For example, that is a freaking high boiling point, right? Okay, so there's some practice problems here. I'm not going to go over them. All the answers with explanations are down here. What you want to try and do is just kind of like try not to look at the answers. Try and do it on your own first and then see if you understand it. I'm not collecting that or anything, but it would be helpful if you do that. Okay, give that a shot. All right. Once you look that over, then you want to do the work for today. The actual work. Oh man, what time is it? Yeah. Just look at that over, and then maybe do just maybe the first free response, because it's already like 12:10. So we went over a lot today. So maybe just do this first free response, and then on Monday we'll finish them. Okay. You could do them all today if you want to, but I'll kind of cut you some slack here. Okay, so we'll talk about these on Monday. Does anyone have any questions? No? Okay, well, go ahead and look over that last part and then do this. Just the first one is fine, and then we'll do the rest on Monday.